So, now that we know about different kinds of stars, it's time to talk about the stellar evolution. What happens to a star in its lifetime, between the time it's formed to the time that it dies? There's a lot of material here, but we're not going to focus so much on all the details. I just want you to get a general picture of how it works. You're going to read a lot of details, but I don't want you to get scared by that. Just focus on the main points and you'll be alright. The first point to think about is that mass plays a huge role in all of stellar evolution. I like to say that big stars live fast and die young. The more mass a star has, the greater the pressure in the center caused by gravity. And the greater the pressure, the faster fusion is happening, and so the faster the star is using up its fuel. Mass determines not only how long a star lives, but also its temperature, luminosity, and size. So mass is the most number one important factor in all properties of a star. So like I said, the more mass a star has, the faster it fuses its hydrogen, and so the higher luminosity it has, so it's brighter, but it also runs out of fuel faster. An O star, the biggest, bluest, baddest star out there, is like an SUV in that it uses its fuel very quickly and will live at most a few million years. An M star, by contrast, the wimpiest red small stars, is like a hybrid, like what's that car, a Toyota Prius. It's going to live for trillions of years, okay, because it uses its fuel so slowly. Trillions of years is longer than the visible universe has existed. So these things essentially live forever. There's some math in the reading that you'll do online. Don't worry about that here. I'm not going to ask you to calculate the age that a star will live to. I just want you to see the differences and understand why. It's a matter of fuel efficiency. Alright, so the life cycle of a star, it's kind of interesting. It all starts with what's called a molecular cloud. This is a cloud of dust and gas containing enough material to make hundreds of thousands to millions of stars. They're all out there in the galaxy. When you look at the Milky Way on a dark, clear night, and you see these beautiful fuzzy patches of stars with dark bands blocking out part of it, those dark bands are giant molecular clouds. And the reason they're dark is that they're blocking the light from the stars behind them. So a molecular cloud is a place where the gas is dense and cool enough to form molecules instead of just atoms. And the gas out there between the stars is known as the interstellar medium, or the medium or stuff between the stars. That molecular cloud will start collapsing and form what's called a protostar. At a certain stage, that protostar will change into what's called a T Tauri star, and then our famous main sequence star will form. And even though it's only one step in this cycle, it ends up being most of a star's life. Toward the end of a star's life, things change and it heats up and swells up and turns into a giant star. Sorry, it doesn't heat up, it puffs up. Actually, it gets cooler. Turns into a giant star. That giant star will eventually eject most of its gas and leave behind what's called a remnant. This could be a white dwarf or a neutron star or even a black hole. The ejected gas will come out in either a supernova or what's called a planetary nebula, which is like a really gentle supernova. And that ejected gas will then go back into the interstellar medium, and it is recycled. It will eventually form new molecular clouds, which will form a second generation of stars. So it starts again. Let's look through some of these cycles, some of these parts of the cycle in more detail. So it all starts with a giant molecular cloud. There's one of these guys in the constellation Orion, which is only a few thousand light years away from us. It's probably the nearest giant star formation region, where molecular clouds are collapsing to form stars. Somewhere in this molecular cloud, there will be a region of gas that's a little bit denser than the regions around it. And if it gets dense enough, by whatever random collisions of gas particles that might occur, it will start to collapse under its own gravity. And as it starts to collapse, bits and pieces of it will then in turn collapse on their own, and each of these pieces will form a star. We know from observations that stars like to form in clusters of hundreds to thousands to tens of thousands of stars. Our star, the Sun, probably formed in a cluster a long time ago. Anyway, once this clump of gas starts to collapse, it's going to heat up, because as the gas collapses and gets closer and closer, particles of gas are going to slam into other particles of gas. It gets crowded, right? And as these collisions occur, the kinetic energy of motion of these gas particles is converted into heat. And this thing is going to heat up to several thousands of degrees. Once it starts to glow in the infrared region of the electromagnetic spectrum, we call it a protostar. Now, we can't see this thing very well, even if it does make visible radiation, because it's going to be surrounded by a cocoon of gas and dust. So we use the infrared or radio or microwave region of the spectrum to look through those cocoons to see these protostars, and they've been directly observed. They also have a disk of material around them, orbiting the star in a disk, and this is thought to be where planets come from, that this disk surrounding the protostar will eventually clean itself up and form into planets. Alright, then after this collapsing continues a bit more, there will be a point at which material will be blown away from the star, from the protostar, in what's called polar jets, because they come out from the north and south pole of the star. The rotation of the collapsing protostar ends up directing, and the magnetic field ends up directing this blown away gas along the polar jets. The first star that was seen like this was the star called T Taurus in the constellation Taurus, the bull. And so stars like this are named after it. They're called T Tauri stars. It's thought that most stars undergo a phase like this, where they blow away a lot of the extra gas and dust around them to reveal the young forming star underneath. The next stage is the main sequence. When the thing collapses enough so that it's reached hydrostatic equilibrium, we say that it's a main sequence star. Remember, hydrostatic equilibrium is where the heat and gravity balance out. And the heat is, of course, produced by the fusion of hydrogen into helium that's occurring in the core of the star, where it's densest and hottest. Most stars will spend 90% of their life, more or less, as main sequence stars. And over the course of their life as a main sequence star, they won't change very much. They'll be very, very stable, like our sun, which is a good thing for any life that's trying to form. They do become slowly a little bit brighter over the course of their main sequence life, but not a lot. Don't think of the main sequence as a step-by-step process. O stars do not turn into B stars or A stars or F stars. If you're a G2 star like the sun, you're going to stay a G2 star for your whole life. You don't change into other types. That's kind of confusing at first. Alright, well, this wonderful life of a main sequence star can't last forever. Eventually, the core runs out of gas. The gas I'm talking about is hydrogen, of course, because it's hydrogen that's the source of fuel for fusion. When the core has been entirely turned into helium, fusion stops. And so, hydrostatic equilibrium is disturbed. Gravity has been patiently waiting for this to happen, and since the heat source is gone, gravity will start to crush the star. And the star becomes denser and hotter in the center as this happens. And then the hydrogen around the helium core will become dense and hot enough to start fusing. And there'll be a shell, a spherical shell of hydrogen surrounding the helium core that begins fusion. Because of the details of the way the shell burning works, it happens a lot more quickly than the normal main sequence fusion inside the core. And so when it turns on, the shell burning causes the star to puff up. The heat source is suddenly a lot stronger than gravity, and it causes the star to expand. And the envelope around the star, the outer part of the star, gets much bigger, causing the star to become what's known as a red giant. And when this happens to our sun in 4 billion years, it's going to destroy the planets Mercury and Venus as they're engulfed by this envelope, and quite possibly the Earth. Definitely, life will become impossible on the surface of the Earth, and this is why one of my advisors in graduate school wrote a song, a blues song, called The Red Giant Blues, that's talking all about how, oh, it's so sad, in 4 billion years, life on Earth will be destroyed. And that's true, but that gives us a long time to enjoy life and to work things out, like maybe traveling to another star.